Well, thank you very much for inviting me to this talk. There's going to be many things I'll say at lighthearted. So I'm going to talk about, first thing is, I'll briefly introduce why I got into it. I'm a circuit designer. I have absolutely no idea about AI, how I got into this. And I'm going to give a couple of examples for each. One is in the education space, basically a review of some of the publications. One of the notable ones is by Professor Razavi on ChatGPT and its use in analog circuit design. And I'm going to talk about some AI tutors that are also very upcoming things. And I'll talk about two applications. That one is digital predistortion, where there have been a very large number of publications coming out recently. And also I'll talk about discovery and inventions, where this might lead us to. So I'll talk about some future projects where this might go, at least my opinions of it. And there's a huge number of people that I have to acknowledge because they helped me put this thing together. Okay, my journey into AI. I see a lot of different kind of things. For example, the Google CEO said it's AI is like electricity and fire. So we have these kind of comments, or of course, NVIDIA CEO basically saying that intelligence is going to become a commodity. So, and then you have things like, of course, Terence Tao, who is a very famous mathematician, won the Fields Medal. He says basically that intelligence and intellect are not going to be the monopoly of humans in the future, and AI is going to change that. Right? And then on the other side, we have things like, AI fundamentally lacks reasoning. It does not understand this, and they're making some efforts to change this and move away from LLMs. So there's quite a bit of effort in that region. And also, economists actually did some surveys, and they found that in the industry, despite all the hype, there's a very, very small improvement in the productivity because of AI. So basically, with all this contradiction happening and me not being in this area, what am I supposed to do? What are we as mortals supposed to do in this area? So I decided I'll become a student and I'll learn as much as I can. And this is essentially my journey into AI, coming from a field that is quite far away from AI. Okay, so just as I started getting into one of the feedbacks I got from Professor Sahar, she's a professor at UCSD. She's one of the best teachers our department has, won teaching awards, and all my students just love her, they come to me. So also I got a lot of emails, messages, from Gabriel, for example, saying that AI is just no good for analog circuits. I also get comments like, if we cannot graduate students who cannot do better than AI. Okay. And then, of course, Razavi's article comes up that says the performance, he did a bunch of tests, I think 28 questions or something like that. He used ChatGPT to see how it performs against what is obviously known in simple 1 transistor, 2 transistor circuits. And then on the other side, Brian Keating, some of you might know him, is a very famous cosmologist at the University of California at UCSD. And his comments were more like, he was complaining about how professors are forbidding students from using AI. They're upset about it. And he basically makes the comment that, we are failing students to teach the most transformative technology that is out there. And he also feels that it's undermining our curiosity, critical thinking, and a whole bunch of things. And there's some choice words he said I will not repeat here. You can watch the video yourself. All right, so there's a further polarization that I saw as I was entering to this. And so I thought, okay, let me go jump in and see what's going on here. Okay, AI in education. So let me give you a little bit of backdrop on this. So as you can see from what is being commented on, and a lot of people said that this is a very bad idea. And but I had a very fundamental problem that I was facing. My teaching assistants in the courses that I teach 3 graduate classes on RF circuit design. And this is a very, very large class. I have almost 100 students. And the TA basically spent over 30 hours, and he was getting paid 10 hours. So the workload is enormous that he is doing. And these are very sincere students who are taking away a lot of time. So I thought, okay, let me first look into this a little bit more. And so I'm going to look into that, but first let me give you some backdrop in what was told, in what was published, because obviously Razavi is a hugely influential figure. So I ended up, his quick summary was that ChatGPT, when he tested it, it did about 40%, which you would probably consider a failing grade for most classes, or at least it would be very close to F, let's say. And he identified some of the problems what AI was doing. So I kind of suspected something was not quite right in the approach that he took. So what I did was basically I had my students simply take the figures and generate a netlist and just replace the netlist, and we did not change a single thing, nothing. Every word for word, we actually used the same approach. And what you'll see that once we did that, the results actually changed from 40 to 93%. And Cloud actually did, and the Gemini Pro even did even better. So one of the things folks will say is, you might be suspicious, saying, wait a minute, Razavi published a paper last year, you're testing it today, the whole world has changed. So I took some help from the AI experts that I was working with, and we were very careful first to check that ChatGPT 5.2 that we were actually testing on was trained with information only until August 31st. So it rules out any possibility that it could be trained. Furthermore, basically we use thinking mode and disable the web. That means it cannot access the web and get new information. Right? And there's also a very important thing you need to do when you use ChatGPT is it often looks at your history, whatever you have in your chat that you saved, it looks at all of that knowledge and assimilates that and answers the question. And that would obviously be an unfair representation. So we disable that. So we spent quite a bit of time to make sure that we are replicating exactly what Razavi did. And we did it actually, I haven't presented all the details, but we did it in so many different modes. There's also 5.0 or 5 that he tested on. So that's no longer available, but we enabled it through API, and we actually tested that also. And the results are slightly worse, but not that much, by a few percentage. So this was my first thing is, yes, ChatGPT is not everything, AI is not everything, but it's also misleading to just take something that has been done and take their word for it. Instead, we should try to do something on our own to figure out what actually is happening. Okay, so then, as you may remember, I got this feedback saying that we should never graduate students who cannot do better than ChatGPT. So just out of spite, I thought I'll go test this. So I basically took 164, which was a foundational course on analog circuit design for undergraduate students. And there are multiple questions that had lots of figures in it. And so we did exactly the same thing. We actually took every circuit, converted that to a netlist, and we fed exactly the same questions. And in all of these, we never helped the AI in any way. We just replicated it as closely as possible. So overall score is 80%. And we got the same score, surprisingly, to my surprise, with figures or with netlist. We didn't see a big difference. And I'll comment on that a little bit further. But first thing is notice is that this particular result shows that it can actually do better than an average student by 1 sigma. That's not bad. If you really use the metric that people are proposing, you're going to be failing 60% of the class. I mean, you could argue that's the right thing to do or not, but it's certainly not true that AI cannot do better than an average student. It does way better than an average student in the exams that are being given to students. You can always trick it, but just as an exam, I really do not believe that AI cannot actually compete with an average student. It certainly cannot compete today with A+ student, for sure. But you folks might have heard this. Why is Wayne Gretzky such an awesome NHL player? Not because he sees the puck. He knows where the puck is going to be. He's a small guy. He's not a very big hockey, he's not the typical hockey player who's bulky. He just knows exactly where it's going to go. So it's more important that we keep an eye on where AI is heading rather than where it is today. And that's the spirit of which I actually started looking into this. So you can go through some of these things. Pretty every question that was given, I think Drew Hall may be even here, every one of these questions, it answered 100% correctly. In where it had figures, it had some troubles. We also know where I have a pretty good insight where it's actually having trouble. Very often we notice that when you build a circuit with multiple nodes connecting to the same point is where it was getting confused. And the final thing was removing the figures and replacing the netlist is not the panacea initially we thought. It did not fix anything, a lot of things. It fixed some things sometimes. Obviously, in the Razavi's case, it was phenomenally better. But in the case of some other cases, we found that it wasn't necessarily improving it a lot, or even if it improved, it's very minor. All right, so the second part I was telling you about, the TA was working 30 plus hours. That's a problem that I wanted to address. So I basically formed an agreement between UCSD and Samvid, which is an AI startup company, and wanted them to help us to see where we can go in terms of tutoring, if there's a possibility for that. And given what Sahar, she's an excellent teacher, it really made me nervous to go in this direction. So I said, okay, this is a good time to take risk. Last year I got the Best Teaching Award. So they can't kick me out immediately, at least they'll give me some grace period. So we thought this is a good time for me to launch right into it. What did we do different? A lot of the AI tutors that I've seen people talk about is that they are doing stuff where they simply take and create an interface between ChatGPT and what their classes are. Instead, what we did was something different, which is I basically took all of my lecture notes and converted into knowledge base. And knowledge base is not, just to give you an idea, knowledge base is you don't just take the figures and say this is a straight line going into a triangle, going into cross. That's not knowledge base. So basically there's a software called Manus, which converts figures into knowledge base. That means it understands what an LNA is, it understands what a mixer is, it understands the circuit representations of it, and creates a text-based information that goes into the knowledge base. That company, unfortunately, has been sold to Meta for $2 billion. So we'll see if we can still get access in the future. But that was the first step we did. The second thing we did was we basically took, I didn't do any of these, by the way. The startup company did all this, so because they are the experts in AI. They took all my lecture videos from the previous years, converted them into transcripts, and then created another database. Then they took all the Piazza questions, and one of the best things I did was to make them all anonymous. So we took all the Piazza questions from 2024, converted them, and basically made a database for that. And then it has two ways to interact with the AI tutor. There's one way you can interact is basically with the internal knowledge. You can interface with the internal knowledge, and you can interface with external research. So what we did is once we had all this information, we went back and actually used the 2025 Piazza questions to go test it. So instead of just believing it, it's like, okay, let's go see how well this really works. So we went through that, and it did pretty well, actually. I was kind of surprised how well it did, rather than compared to just natively going to ChatGPT and asking questions. And the two ways students can interact, and this is what's really nice about it, is that they can basically interact through the internal knowledge base. That means it goes and picks up all the information from here, answers your question based on that, not based on ChatGPT. And it also has something called external research, which I absolutely love. What's great about this is you can go to this portal, of course, access ChatGPT, Gemini, all these things. But there's one feature, which is you can take the internal knowledge built and say, do you agree with professor? Oh, what a great feature that is. So you can actually cross-check if what I'm saying is actually true. You can challenge me. And that's a beautiful feature. And I was surprised how many times it actually pointed out what I was not saying was not precise. It goes through the whole thing, and it says, mostly agree, but here are the limitations. For example, it'll point out that, yes, what I said was true, but only for linear systems. Yes, this is true, but blah, blah, blah. It gives a lot of nuanced responses, which is actually very helpful to all this. Because in a class, you assume a lot of things, like an inherent knowledge base that you assume it to be true. So basically, we implemented this in 265 and 265D, and we're going through the process now to test how well it works. The quick summary is that what I really loved is, unlike ChatGPT, it actually mimics the way I talk, the language I use, which is kind of bizarre, to be honest. When I read that response, it seems like I'm actually responding to it. There are some things that are not good about it. Like, for example, it gives links to the chapter 2. For example, students are asking on chapter 2 about difference between QAM, PQ, PSK, blah, blah, blah. It's very good at saying, professor is right, but he's not right that for QAM and for QPSK, there's no difference, which is it's true, because they're exactly the same. It's able to pick up so much kind of nuance once you connect it with external knowledge base. But I like the fact that it actually talks just like me. They're giving the responses that mimic that. And I also like the fact that you can actually challenge the professor and use this external knowledge and correlate all the information. So it's an interesting experiment we've done. Okay, so let me get into digital pre-distortion. So this is more on the research side of things. So for folks who are not familiar with it, power amplifiers are extremely nonlinear. So if you put an input, you get a huge amount of compression, which is not very desirable because it creates EVM problems, ACLR problems, bunch of issues. So what we really desire is we want to, even though the power amplifier is nonlinear, we want the output to be completely linear. And the way to do that is we basically do something called pre-distortion, which is you can think of this curve, for example, if it's square root of x, you put in x squared, runs through the whole thing, you cascade, you get a linear function. That's the basic idea of pre-distortion. So in order to do this, of course, there's a bunch of complicated math on Volterra series, frequency domain and time domain. And I won't go through this that much because I'll explain to you a little bit more intuitively. One of the basic things is applying Volterra to power amplifiers is a fairly complicated affair. There's armies of people working at companies to make this work. And one of the huge challenges with Volterra by itself often is the number of coefficients you have to deal with. And there are some very good ways to deal with reduce the complexity by using memory polynomial, generalized memory polynomial, truncated versus full Volterra. So there's variations of this implementation that will reduce the complexity and trade it off with accuracy. What I noticed is since 2023, there's a huge uptick in the number of publications that are on using AI techniques for digital pre-distortion. So I got interested in that. So like, okay, let's see what's going on. So this is kind of the traditional way of doing DPD, which is you have a feedback receiver that generates, that has the output power, you tap some of the power from that, and you basically train using the Volterra coefficients. You can train the DPD block to essentially generate the inverse function. And once that is done, you can now send those signals through the PA, and you should get a very linear output. The main advantage here I want to focus is not just only make it more linear, you actually, in return, get better efficiency of the PA. The goal is more the efficiency. So you trade off that, and you try to get back more efficient PA to operate. And there's a couple of ways to do it. Of course, there's the more Penrose method, which is where it gives you the global minimum very quickly in one step, but it's a very high level of complexity. Often gradient descent is what is implemented in mobile platforms. And then the new AI technique that it's there in the reference paper I've actually quoted here. So the same thing, instead of actually generating using Volterra approach, you basically have a power amplifier model, which is essentially a neural network. And that neural network, you know what is being sent, because obviously your transmitter is sending that. You know what is being received, because at the power output of the PA, you basically detect that signal, digitize it, and you know exactly what the bits, what is being sent, like I of t, Q of t, and you know how I of t and Q of t are shifted from the intended target. So by comparing these, basically this power amplifier model essentially looks at what is being sent, what is being received, compares the two, and essentially adjusts the neural network parameters to generate a PA model. Once you have a neural network PA model, then you can actually take and have a DPD model, which should be an inverse function. So you freeze that PA model, and you put a DPD neural network model here so that its coefficients are trained so that you can actually generate the inverse function. And there is some loss factors and all these things, but the basic idea is you have your PA model that is frozen, and you put another neural network here to generate a DPD model, which if you use, will give you a completely linear operation. Right? So you got a square root of x, you generate x squared. Once you know it's x squared, then you can just use x squared. Okay, so, and of course, when I showed all this math to, by the way, the work done here was based on STTR. That's a project we got from some funding. And when I showed this thing, it's like, Prasad, tell me in like more regular words. This is too crazy. Like, okay. So you can think of its relationship to AI as the following way. So ChatGPT has been trained on a very, very large database. So when you write something like Zurich is, of course, it can prompt you the next word, right? So think of, and the more, more information you have, the more precisely, and it can fill in these blanks. And what it's doing for DPD is not that different. You have a waveform that you want to send, but because it went through the PA, it's got distorted. It's not the same as what you sent. Therefore, you can actually use this information essentially to figure out what you need to send in order to make it a completely linear system. So it's in that way, you can basically have, that's the simplest explanation I can give, to make sure that we can get a linear output. We change the input in order to get a completely linear output. Right? So one of the good things, at least this is what being discussed in the papers, and I'll tell you some of the weaknesses also, what people are talking about. So the supposed benefit of this is it has an ability to generalize rather than being very specific. I honestly think we're a little bit farther away from this, and I'll show you some results. So OpenDPD is a really, really good group that one of the best things that they have done is they actually took all of the measurements they did, they put it on GitHub, they put all their code on GitHub, so you can simply download and just reproduce the results. So that's what I did, and they use this LSTM algorithm. LSTM is long-term, short-term. That's a precursor to transformers. So they were the king in AI world before transformers came along. And the way it works is long-term memory. Basically, you can think of in a power amplifier, the RMS power belongs to the long-term memory. Based on the average power, the biasing of the PA, a lot of things depend on that, but they're averaged over a much longer period. And the short-term memory is more like an envelope of your amplifier. So it's what happened and what peaks and all those things you hit recently, those all belong to short-term. And they showed that basically that you can implement this, and the power amplifier input in blue is the pristine input. And then after you went through before any pre-distortion, you see the orange. You can see that it's pretty bad. And after you use the GMP models, which are pretty standard traditional ones, you can see that the distortion has been reduced. And using the LSTM algorithm that they've developed, you can see that the performance is even better. So I was a little suspicious. So one thing is I had my students download this, literally run it exactly what they did, and I did generate exactly the same data. So at least they weren't bullshitting. So okay, I was convinced, okay, let's do this. And we kind of filed the research proposal based on that. And basically over the last few months, we got some results. We took their algorithm, we went to the lab, we implemented exactly the way they implemented, and you can see that the performance is also pretty good. We are able to improve the distortion and lower, but the few things that this was all trained on what is called a 0 dB backoff, that's a maximum power. One of the things that I have not seen the papers do, and I think this is where some of the gaps need to be covered, is that they train on one power, they test at the same power. And I felt that's not really realistic. So we went to the lab and said, let's back it off. Let's go back off by 2 dB, what happens? Let's back off by 4 dB, what happens? Let's back off by 6 dB, what happens? And you can see that the performance is not the same. Of course, the distortion itself comes down, but it's not really the same. So there's some work that needs to be done. The second thing I see is that if you look at the faraway noise, you see that it actually got worse. And there's a very critical spec in most of the cellular system that particularly impacts the receive band noise, GPS noise, outer band emissions. So the reason you didn't see that in the publication is because in the publication, they only showed the next channel. So it's like going to this and cutting it off directly here. Of course, you won't see the other parts, right? So, I mean, this is what you learn when you go actually repeat and do what people have done, right? So this is kind of one of the proposals we put together for the phase 2. It's kind of what I envision as what needs to be fixed. So single data points, yes, DPD is working very well, I agree. I tested it, I'm pretty confident it can actually do as well. But there's a lot of things that you also need to do, which is we need to make sure that it works for different carrier frequencies within the band. We need to make sure it works for different bandwidths. Those are the common ones, not that big a deal. But we also need to make sure it works for different output powers. So that's something we cannot ignore. We need to make sure it works at different temperatures. A few improvements are being made. I noticed some of the papers now train on one PA, they get another PA and test it. That's the right thing to do. Don't just test it on the same PA. I also think we need to make it based on bias current because the PAs often have a way to bias the current to optimize the power. Of course, they change supply voltage, and not to mention envelope tracking. We need to make sure that different waveforms with different peak to arrow ratio, because if you send one subcarrier versus 100 subcarriers, the PAPR will be very different. So there's a lot of work actually that needs to be done. So I kind of summarized here all the same points. However, even despite this, for AI techniques to work better, there's several things one needs to actually focus on. That whatever is done here needs to be better than the traditional Volterra method or pruned method. It just can't be that, oh, AI did the same thing. That doesn't fly. So it really needs to improve over the performance itself. So let me talk about what some of the things. There are a few nuances also one needs to be careful about, is that when you implement this, you can't use the energy of the universe to implement AI and make it better. You need to also be low power. So mobile readiness is something very, very important in order to pull this off. So the classical DPDs, I'm going to go a little bit quickly here. They don't usually use CPU and GPU. They instead use basically what's called L1 cache, which is a DSP and memory that sits right close to where the TX signal is being sent out. Right? So I've done some quick estimations on this. And there are some papers that are also published on this. So what the key takeaway is that the DPD algorithm that was developed needs to have not a million parameters. That is not going to work because it cannot fit in the footprint of a L1 cache. So one of the things they have done is they made some effort to make sure it fits in a small cache within so that it can be actually implemented. And it's in such a way that it doesn't add much overhead to the existing architecture. That means the remaining things will take up about, say, 50K of cache. This can add another little bit more, but it cannot completely undermine it. So even though you have 50K cache, you can't just put another 50K on top of it. That has a lot of detrimental impacts. Okay, so this is like a high level of where does AI DPD can succeed? So one place I feel it can succeed and where it cannot succeed. If you take narrowband, if you have something that doesn't have a lot of memory, I feel there's just no chance AI can actually help you here. However, if you have situations where there's extreme nonlinearity, the problem with Volterra approach, as good as it is, the number of coefficients just explodes. And that becomes a huge bottleneck. And this is where AI actually, one good description often some people are giving me is, AI is just a great nonlinear curve fit. That's what it can do. So this is an area it can actually work. And there are some special cases, two things that I know and that I'm working with some of the companies. One is in the application of radar where the power is insane. It's really, really high. So it creates a lot of nonlinearity. The other one is some people are interested in LPA, LPDD. LPD, this is basically not being able to detect. They take a signal that's 10 megahertz, spread over 1 gigahertz of bandwidth, so it just looks like noise. The memory effects are massive in these cases. So these are the two cases I think it can actually work well. Okay, AI for research. Am I out of time? Should I stop? Stop. Okay, all right. I have some stuff on invention and discovery, but I'm out of time. Thank you very much.